Hello, I'm Alastair Donaldson and I'm a lecturer in the Department of Computing at Imperial College London. I'm the leader of the Multi-Core Programming Research Group and I'm also coordinator of CARP, which is an FP7 funded European project on correct and efficient accelerator programming. During the CARP project, we're investigating a variety of techniques and tools for helping developers in the construction of software to take advantage of accelerator processors, particularly graphics processing units, GPUs. And in the project, we're looking among other things, novel programming models to help developers write high-level code that could be compiled efficiently into low-level code for a range of architectures, and also into techniques to aid in developing correct software, so testing, bug finding, and verification techniques, particularly for low-level software written in languages like OpenCL. During these three lectures, I'm going to talk to you about GPUVerify, which is a technique and tool being developed at Imperial as part of CARP, and in collaboration with various members of my research group, and also with Shaz Kadir at Microsoft Research in Redmond, USA. In the first lecture, I'm going to give you an overview of GPUVerify and how it can be used to verify race freedom of OpenCL and CUDA kernels, going through various demos. And then in lectures 2 and 3, I'm going to dig into the technical details of how the technique works. So to start with, I will give an overview of GPUVerify. So a graphics processing unit, or GPU, is a massively parallel processor which was initially designed to accelerate graphics computations, but these days has found application in various domains such as financial simulation, physical simulation, media processing, and a variety of other areas. So I'm now going to give you a brief overview of a typical graphics processing unit, and if you're a GPU expert, you'll realize that a lot of the things I'm saying here are not strictly true for all GPUs, but my idea here is to just give you an overview of what these architectures are like in order to explain how GPUVerify works. So a GPU consists of a number of processing elements, which are a bit like cores, and each processing element has a small amount of private memory in which it can store data that it should operate on. On the GPU, there are many processing elements, and the processing elements are organized into groups, such that processing elements in the same group have access to a shared portion of memory, which is called group shared memory, or sometimes referred to as local memory. In addition, there is a pool of global memory, which all the processing elements on the GPU can access. Now, a GPU is used to accelerate a system comprised of, say, a multi-core PC by having the GPU plugged in as an accelerator card. And the way this works is that the multi-core PC, so here I'm showing you a PC perhaps with 8 cores, the multi-core PC copies data to be operated on and also code to be executed into the GPU's global memory. The host then says to the GPU, go, and invokes a kernel function which runs simultaneously on all the processing elements of the GPU. So this lights up the processing elements. They crunch through the data by copying data from global memory into the group shared memory, and from the group shared memory into private memory. And then when they're finished, they copy data back into global memory. And then the host is interrupted, and the host can copy the data back into its memory for further processing. And in a GPU accelerated application, there might be just one call to a GPU kernel to accelerate one piece of computation, or there might be a series of kernels that are pipelined together to perform some task, or there might be a loop on the host with a kernel invocation inside the loop, perhaps to do some kind of iterative computation where you want to do a kernel for every time step until you converge to a fixed point. So that's a brief overview of what a GPU accelerated system looks like. When writing a GPU kernel, a programmer needs to pay special attention to making sure that threads running on different processing elements interact correctly with each other, and in particular they must not interfere with each other. And a very common way in which threads can interfere with each other is via data races. So we can have an intra-group data race if threads running on different processing elements in the same group access a single element of group shared memory, and at least one of these accesses is a write. So if there's no synchronization between these accesses, there's no guarantee as to which order they will happen in, and then we have an intra-group data race. And we could also have an intra-group data race on global memory, which I've not shown here. Another kind of data race is an inter-group data race, where threads running on different processing elements in different groups have access simultaneously to a portion of global memory, and at least one of these accesses is a write. So this is an intergroup data race. So data races in GPU kernels lead to all kinds of problems. They make the execution of the kernel non-deterministic, and this is the same in regular concurrent programming. However, a key difference between regular concurrent programming and GPU kernel programming is that data races in GPU kernels are almost always accidental and unwanted. So if you're familiar with programming with p-threads, say, often data races signify bugs, but it can be quite common for programmers to have deliberate data races for purposes of optimization. Now, in my experience of looking at GPU kernels, this is not the case. There are some cases, which I will actually come to later, where there's a benign data race, say where threads are guaranteed to write the same value to a location, in which case there won't be any non-determinism arising from the race. But I have never personally seen an example where there's a deliberate data race in a GPU kernel that would lead to non-deterministic behavior. I'm sure some examples exist, but it's a very rare situation. So this really motivates techniques and tools for helping programmers to eliminate data races from their software. So at Imperial, we've been designing a technique and tool which we call GPUVerify, which is a tool for verifying that GPU kernels are free from data races, and also another kind of problem called barrier divergence, which I will talk about more in a later lecture, although I will show an example of barrier divergence later in this lecture. And GPUVerify is designed to analyze kernels written in the two main programming models, OpenCL, which is an industry standard general-purpose heterogeneous programming model that mainly targets GPUs, and CUDA, which is NVIDIA's proprietary programming model for programming their classes of GPUs. So I'm now going to give you a demo of GPUVerify in action by writing some simple kernels and showing you what the tool will do. If you'd like to try GPUVerify yourself, you can go to the tools webpage, which is from the Multi-Core Programming Group's homepage, and you can see some documentation. You can download the tool and try it out. And like I said before, GPUVerify is being developed as part of the FP7 project CARP. So go to the CARP webpage shown here if you would like any more information about the CARP project and latest news. I'm now going to give you a demo of GPUVerify in action by writing a simple OpenCL kernel. I start by writing the kernel keyword. A kernel doesn't return anything, and I'm going to call this kernel add neighbor. As a parameter, this kernel is going to take a pointer to an array of integers, A, and I want this array to be allocated in group shared memory, so the memory shared between processing elements in a group, so I'm going to give it the local qualifier to say this in OpenCL. The kernel is also going to take an int parameter offset. Now, when the kernel is invoked on all the threads of the GPU, every thread runs the same function and they all get the same value parameters. So every thread gets the same pointer to A, every thread gets the same value for offset. However, threads can do different things by querying their thread ID. In OpenCL, there's a built-in function, getLocalID, which gets a thread's ID within its group. And in OpenCL, kernels can be 1, 2, or 3-dimensional. During these lectures, I'm just going to consider 1-dimensional kernels, although the tool does support 2- and 3-dimensional kernels. And if you want your ID in dimension 0, you say getLocalID 0. So we're going to use getLocalID 0 for TID during these lectures. What this kernel is going to do is it's going to write to A at TID, and it is going to increment A TID by A of TID plus offset. So it's going to add the value held by some neighbor for A. And to make this a little bit more readable, I'm going to hash define TID to be getLocalID 0, and then replace getLocalID 0 by TID throughout the kernel. Now if I go to another window, I can run GPUVerify on this example. So if I say GPUVerify kernel.cl, the tool will first complain and say that the work group size hasn't been specified using local size. So in GPUVerify, we're not doing parameterized verification. We try to verify that a kernel is free from data races for a fixed number of threads, but it can be a very large number. So for example, we can run GPUVerify saying that local size is 1024. And we also have to say how many groups of threads there are. So in this case, we could say that the number of groups is also 1024. So we're verifying this kernel for upwards of 1 million threads. So if we say go, GPUVerify now analyzes the kernel, and in a short period of time it reports a possible data race, which actually is a genuine data race that could arise when executing this kernel. So it's saying here there's a possible read-write race on A at byte offset 4. Okay, so this is like A1 if you think about A being indexed at int boundaries, or A4 if you think about A being indexed at byte boundaries. And it's saying that at line 5 there might be a write by thread 1 of group 0 and a read by thread 512 also of group 0. So you can imagine that thread 1 and thread 512 could have a data race if offset was let's say 511, okay? That way, thread 1 could be reading from 512, while thread 512 writes to 512. So this is a genuine data race that could arise when executing this kernel. If we go back to the kernel code, we can eliminate this data race by using a barrier. So we can define an int temp, and we can take this expression a tid plus offset, and we will pre-compute this into temp. And then we can write a barrier call. And this parameter CLK local memfence says that this is a barrier on local memory. So what this does is it says that all threads should run until they reach the barrier, and then they should wait there until everyone gets to the barrier, and then they should all proceed beyond the barrier. And the local memfence argument says that local memory reads and writes will have completed by the time anyone proceeds past the barrier. So it's now safe to read temp because this read will have completed. Okay, so we're not going to be interfering with another thread who's writing to tid. So with this fix, we now run GPUVerify again, and it will tell us that the kernel is okay. So what it says here is that there are no data races within work groups, so none of these intra-group data races, no data races between work groups, no barrier divergence, which I'll talk about briefly in a minute, and also no assertion failures. I haven't specified any assertions, but the tool can check for programmer-specified assertions. And then the tool also says that there's absolutely no warranty provided because this is just a research tool we've been developing at Imperial, so don't use it to verify your GPU-accelerated aircraft, for instance. Okay, if I go back to the original structure of this kernel, where we were writing to tid and having this concurrent with reads from tid plus offset. And then if you think about it, there are certain values of offset for which this kernel is correct. In particular, if offset was equal to the number of threads in a group, this kernel would be fine. Okay, so every thread would be writing to a tid and reading from a tid plus number of threads. And for two distinct threads, these accesses are going to be disjoint. So let's define n to be get local size 0. And now we can say here that we know that this parameter offset is going to be equal to n. So what we can do here is we can add a requires annotation, which is something we've added in GPUVerify, to say that this kernel has a precondition that offset equals n. Now, if I go back to the other window and run GPUVerify again, even without the barrier, this kernel will be proved free from data races because it's impossible, as I argued to you already, for there to be a race if offset is equal to the number of threads in a group. If we made a little error and said that offset was equal to n minus 1, then we would expect an off by 1 data race. So if we run the tool again, let's have a look and see what happens. You can see here we've got a data race where thread 1023 interferes with thread 0. So this isn't too surprising because there are 1024 threads and there's an off by 1 error, so we've got a problem involving thread 1023. Okay. If I fix the problem again, you might observe that actually if offset is any multiple of n, this kernel is going to be okay. It doesn't have to be equal to n, it could be any multiple of the number of threads. And we can specify this in our precondition. We can say something like offset mod n is equal to 0. And with this precondition, we verify the kernel, and it should be verified free from data races. Yeah, there we go. And again, if we made a little mistake and we said that actually offset mod n was equal to 1, this wouldn't work out, and a data race will be reported. Okay, so now we've got a write by thread 1 and a read by thread 0. And if you think about it, there are certain values of offset that would satisfy offset mod n equal to 1 that would cause this data race to happen. You might have noticed that all the races reported so far have involved threads in group 0, but we've said there are 1024 work groups. So you might wonder, is it possible for races to happen for threads in different work groups? In particular, could a race happen for a thread in a high work group? So what we can do just to experiment with this is we can add an assume statement here. So I should say, by the way, that the reason we get group 0 is because there's a constraint solver underpinning GPUVerify. In this case, it's Microsoft's Z3 constraint solver. And we just get whatever values the constraint solver gives us when we ask what the problem is. There could be many, many possible data races, and we just get an example from the constraint solver. But if we want to ask, would it be possible for there to be a data race with threads in higher groups, we can add an assume statement here and say, assume that get group ID 0 is, for example, larger than 400. Could there be a data race between threads in larger groups than 0? So if I rerun the tool now, then is giving me a potential race between threads in group 401, for instance. Okay? But still, we've got thread 1 and thread 0. So now I might ask, just to show you as an example, can it be that there could be a data race if the local ID is larger than 10, for instance? So running the tool again. Now the constraints level will give us values of threads with IDs larger than 10 if they exist. So here, for some reason, it's given us thread 265 and thread 264, both in group 401. So these assumptions just let you play with the tool and see what kinds of bugs can happen. So you might say, okay, there could be a data race. I would like to know, is it just for one pair of threads or could it be for various other pairs of threads? And you can experiment using assume statements. But you have to be careful because if we have inconsistent assumptions, like say I assume that get local ID 0 is also less than 10, I'm now asking GPUVerify, can there be a thread whose ID is greater than 10 and less than 10 such that a data race occurs? And because no threads satisfy this condition that their ID is both larger and smaller than 10, then there can't be any data races, and GPUVerify will now tell us, correctly given our assumptions, that the kernel is okay. So if you use these assumes to experiment with the tool, you need to be very careful. You need to make sure you don't introduce inconsistency, otherwise you get vacuous verification results. I'm going to move on now and show you an example written in CUDA, which is also supported by GPUVerify. So let's open kernel.cu. And here I'm going to write a very simple reduction kernel. So in CUDA, we have to hash include the CUDA header file. And then we specify that a function is the kernel entry point by saying global. So global void reduction. And what this kernel is going to do is it's going to take a pointer to an int. And in CUDA, this is implicitly in GPU global memory. So CUDA doesn't have a keyword to specify this. And what we're going to do now is say that we're going to loop using an integer d, which is going to initially be half the number of threads in a block. So d is block dim.x divided by 2. We're going to loop while d is greater than or equal to 0. And on each iteration, we are going to divide d by 2 by right-shifting it by 1 bit. And then in the body of the loop, we're going to say that if my thread ID, which in CUDA you say thread idx.x, similarly x is for a one-dimensional kernel. If my thread ID is less than d, then I am going to increment a at my thread ID by a at my thread ID plus d. And like I did with the OpenCL example, for convenience, I'm going to say hash define thread idx, sorry, hash define tid to be thread idx.x. To make this a little bit more readable, and I will also use n to denote blockdim.x. Okay, so what this does is it says that first of all, half the threads are enabled, and every thread whose ID is less than n over 2 will read from the thread tid plus n over 2 and update a tid by summing the current value with that value. Okay, and then half the threads will drop out because d will now be n over 4 once we right shift it by 1 bit, and then a quarter of the threads will sum up what they've computed so far with what their neighbor n over 4 places away computed, and we will keep halving the number of threads until finally there's only one thread left which will sum the value from its right-hand neighbor, and we will get the reduction of the array. So we will end up with a0 being the sum, the end value of a0 will be the sum of all the values of a at the start of the kernel. So if we run GPUVerify on this example, we have to now say that block dim equals some value, let's say 1024. Okay, and this kernel only makes sense for one block of threads because it is writing to an array in global memory. So we're going to say that grid dim equals 1, kernel.cu. So we let GPUVerify think about this, and it will report to us a possible data race. So it's saying that there are various possible data races, but in particular at line 11, thread 0 of group 0 could race with, by reading with a write, also at line 11, by thread 32 of group 0. So if we look, this is line 11, okay? And the problem is between thread 0 and thread 32. But if you think about this, there's no synchronization here. So it could be that one thread could race on and do many loop iterations while another thread is still on the first loop iteration, and there could be races between loop iterations. So the problem here is that we're missing a barrier synchronization to protect threads from each other. So let's add a call to sync threads, which is CUDA's barrier function. So if I have this call to sync threads and run GPUVerify, let's see what happens. GPUVerify is now going to tell me that there's an error at line 12. A barrier may be reached by non-uniform control flow. So if we look at line 12, this sync threads, the tool is saying, might be reachable under non-uniform control flow. And what this means is that there could be threads in the same block that follow different control flow, and some of those threads reach the barrier and other threads don't. So this is an example of barrier divergence. And we can see here that it could occur because only threads whose TID is less than D will reach this barrier. Other threads will keep executing the loop. And the rule is that all threads must get to the barrier before any leaves the barrier. And this is clearly not going to happen here. So this is a problem. And this was a deliberate mistake where I put the barrier inside the conditional, whereas really the barrier should have gone here. Okay, so now if I run the tool again, all being well, it should now report that the kernel is free from data races. Okay, good. Now, you might observe that we guaranteed in our loop here that D would always be a power of 2. And we might want to assert this in the loop body as a sanity check, or to document the kernel so that if someone was coming to read this, they could understand our intentions. So we can use an assertion to say that D is a power of 2. Okay, and I'm going to write a little macro to help us here. I'm going to say that is power 2 holds for X if when we take X and we bitwise AND it with X minus 1, we get 0. So if you think about it, a power of 2 in binary representation has a single bit set to 1. All the other bits are 0. Okay, so if we take a binary number and subtract 1 from it, we get a 0 where the 1 was, and we get 1s everywhere else. And if we bitwise AND the original value and the value minus 1, we're guaranteed to get 0. Okay? And this can only happen if the value is a power of 2, or if it was 0, because clearly if we bitwise AND 0 with anything, we get 0. So if we want this to really say that X is a power of 2, we have to say that either this condition holds, so we have to say this condition holds, and furthermore, X is not equal to 0. Okay? So this is our is power 2 assertion. So I'm going to run GPUVerify and ask it to check that on every loop iteration, D is a power of 2. So if I run the tool, let's see what happens. It's telling me here, line 12, column 9, an assertion might not hold for thread 5 of group 0. And it's this assertion about D being a power of 2. Okay, so this seems a bit strange. Clearly D is a power of 2. Why wouldn't the assertion hold? So what we can do to investigate this further is we can actually run GPUVerify in bug finding mode. So if I run this command and I add the parameter find bugs, what GPUVerify does now is it unwinds loops a little bit, but it doesn't employ any kind of abstraction, and it looks for defects. And here it's saying that no defects were found, okay? And it's giving some advice. It's saying use loop unwind equals n with n larger than 2 to search for deeper bugs, or rerun in verification mode to try to prove absence of defects. Well, we already tried running it in verification mode and it complained, so let's look for deeper bugs. So we could try loop unwind equals, say, 4. Okay? Unwind the loop by 4 iterations. Does the tool find any problems? No, it doesn't. Let's try 8 iterations. Does the tool find any problems? Again, no. So now we don't know whether this is a problem that GPUVerify just couldn't prove the kernel correct, or actually if there's a problem with the kernel. But let's try one more. Let's try loop unwind 12. And in this case, because I designed this example, I know that GPUVerify will now find a bug. It says that an assertion might not hold for thread 768 of group 0, and it's this assertion. Okay, so what this tells us is that the assertion genuinely can fail because GPUVerify isn't employing any loop abstraction. It's actually unwinding this loop and exploring the thread's interleavings up to some loop depth. That's not strictly true because, as I will explain in future lectures, there is some abstraction of the shared state going on. So it could still be that this could be a false alarm. In this case, it's not, because if you think about it, we've said here that the loop will iterate while D is greater than or equal to 0. Okay? And in particular, the loop will iterate when d equals 0, and this assertion will fail. And furthermore, we don't really want the loop to iterate when d is 0, because when d is 0, no thread's ID will be less than d. So there will be a totally redundant loop iteration and an extra barrier synchronization. So this is actually very wasteful to have d greater than or equal to 0. So if we now fix this and make it d greater than 0 and rerun GPUVerify with loop unwind 12, and because I fixed the problem, it should come back and say that no bugs were found. Okay? And now it's worth us trying to rerun this in verification mode. So if I remove find bugs on loop unwind, it's now actually trying to prove that this kernel is free from data races. And in this case, it succeeds in doing so. Now, the last example I want to show you in this lecture is a case where GPUVerify can tolerate a kind of benign data race in an OpenCL or CUDA kernel. And I'm going to go back to OpenCL mode. So I'm going to open kernel.cl. And instead of add neighbor, I'm going to call this find. Okay? So let me delete the body of our old kernel. So what we're going to do is we're going to take an array of integers. In fact, let's make it an array of floats, because the tool can also work with floating point numbers, although it abstracts their representation, because we can't do reasoning about floats, but in this case we can do some very simple reasoning about floats. And we can say that this is in constant memory. So OpenCL supports the idea of a constant memory space that you can't modify. So we've got an array A, and we've got an int, we've got a float value, which is a value we'd like to search for in A. We've got an unsigned max, which is going to tell us how big A is. And finally, we've got a pointer to an int called found. Okay? And we're going to set found to true if some thread finds that value is in the array A. So we can write this kernel pretty simply in OpenCL. What we can do is we can loop for int I equals 0, I less than max divided by the number of threads, I plus plus. And on each loop iteration, what a thread is going to do is check whether it finds value at a position relative to the current loop counter I. So we're going to say if A at index I times the number of threads plus tid, so on iteration 0, thread 5 would look at A5. On iteration 1, thread 5 would look at A1029 because there are 1024 threads. Okay? If this is equal to value, then found is set to true. And actually, let's make found be a Boolean to make this a bit more readable. Okay? So if we find the value, then we write to the memory location that found points to, and we write the value true. And now, we can also test here whether found holds. So if found holds, we can break the loop. We can in fact return from the function. Okay? So in this case, the value has been found in the array. So what we can do here is we can say at the beginning that found is false. So this means that every thread is going to set found to false. We could just have thread 0 set found to false, but then we would have to say, if my ID is 0, set this thing to false. Or we could just have everyone set it to false, in which case there are going to be data races on found, but everyone's going to be setting it to false, so these data races don't matter. Okay? So we can then do a barrier. So everyone sets found to false, and then we know here that found is false. Okay? And then everyone checks their current element of A, and if someone finds that A matches value at this position, they set found to true, and it doesn't matter if 7 of them find the value holds or 9 of them finds the value hold. Found is false, and they're going to set it to true, and it's okay if many of them set it to true, because setting this thing to true is an idempotent operation. And then they can synchronize. And then they can check whether they found this thing, and if they did find it, they can return from the kernel. Okay? And then they can synchronize again. So here we have got, let me make this a little bit smaller so you can see it all. So we've got a benign right-right race where all threads are setting this into false. And then we've got a benign right-right race where some threads are setting this thing to true. Okay? So if I run GPUVerify on this example, local size equals 1024, num groups equals 1, kernel.cl, then it should say that this kernel is okay. It shouldn't mind these benign right-right races. Okay, so you can see that it said things are all right. If we don't want it to tolerate benign races, we can turn this off. So we can say no benign. And now we will get some complaints. So for example, it's going to complain that at line 9, column 5, there could be a write by thread 0. This find becomes equal to false. And at line 9, column 5, there could also be a write by thread 1. Find becomes equal to false. So this is no surprise to us. This is this line where they're all setting this thing to false. And similarly, it's giving us a problem at line 13, where find has become equal to true, in this case, between threads 0 and 1. And these are just examples that the race could happen between actually any pair of threads in principle. All right. So if I turn benign race checking, benign tolerance on again, this will be verified. And just to show you there's not some funny business going on, if I said instead of found becoming true, I said that found becomes equal to tid, then GPUVerify should not be happy because the threads are going to write their ID, which is different between different threads. So all being well, this should now fail to verify. Okay, there's a problem here with different threads writing their TID. So this is a little example of GPUVerify being able to verify race freedom for something that can find elements in an array and tolerate benign races. So you don't have to add extra barrier synchronizations to make your program verify. And this is very important if you want to get high performance from your kernel. So that concludes my tour of GPUVerify and the overview lecture. And in the next lecture, I'm going to start digging into the details of how the technique actually works behind the scenes. Thanks for listening.